Hello and welcome back. This video is limits via sequences, and I'm Dr. Joseph. In this video, we'll think a little bit harder about the definition of a limit, what a limit really is. So it starts with a sequence. Sequences of numbers are just infinite lists of numbers, and everybody knows what a sequence is, right? We can just have the counting numbers, 1, 2, 3, 4. We know that goes on forever. The square numbers, the prime numbers, Fibonacci numbers, the digits of pi. We're going to be thinking more often about sequences where the next term is coming from some rule that depends on where you are in the sequence. So xn is like the nth term of the sequence. And here's an example where the nth term is n squared plus 1. So then the first term is 1 squared plus 1. The second term is 2 squared plus 1, and so on. And you can work out that comes out to 2, 5, 10, etc. Here's another rule. Xn is square root of n squared plus 1. So that would eventually create this sequence, root 2, root 5, root 10, and so on and so forth. So there's lots and lots of sequences. And so the way that we rephrase the definition of a limit is going to be in terms of limits of sequences. So we say a sequence converges to a number A if the numbers in this sequence are getting arbitrarily close to A. So eventually the difference between numbers in the sequence and the number A is getting very close to 0. Closer and closer the farther you go. So here's kind of a example that I think is very captivating. You can just take the next number, we'll just tack on one more decimal place of the number pi. So 3, 3.1, 3.14. And if we just fill in one more decimal of the number pi, that's going to get closer and closer to pi. So you would say this sequence converges to the number pi. Another silly example, just start with 0.9, add on one more 9, and then another one, and keep doing that forever. These numbers are getting closer and closer and closer to the number 1, and eventually they'll be within any tolerance level. So here's another sequence, 1, 1/2, 1/3, 1/4, etc. What is this sequence approaching? Think about it for a minute. The numerator is always 1, the denominators are getting larger and larger. So these fractions are approaching the number 0. So here's the definition. We say that the limit of f of x as x approaches a is equal to c. If as x values get closer and closer to a, the y values get closer and closer to c. This is the definition we had on the last video. So think for a moment, maybe pause the video. What does this have to do with sequences? How could you rephrase this using sequences? And here it is. So we say that the limit of f of x as x approaches a is c if for any sequence of x values approaching a, so this is x1, x2, x3, and the limit of that sequence of x values is a, we can plug all those x values into f and look at the sequence of y values, f of x1, f of x2, f of x3, and see if that sequence is approaching any number at all. And if that sequence is approaching C, and then also for every possible sequence approaching A, the sequence of Y values approaches C, that's what it means for the limit to be C. So that's a lot. And you might be thinking, well, how could you ever possibly check that? And luckily we don't have to, but it's helpful to know this when you're analyzing graphs, especially when limits don't exist, as we'll see in the next couple of slides. So it's really important. This needs to hold for any sequence of x values approaching A. So here's an example that you saw on one of the previous videos. And all I've done is add in a sequence of x values. Here's x1, x2, and a whole mess of them, right? They're approaching 3. So there's infinitely many points there, even though I haven't drawn them all. They're getting closer and closer and closer to 3. And so I have one sequence of x values approaching 3. I want to look for those x values where are the corresponding y values. And I think my screen share stopped for a moment. And we're back. Sorry about that. So we're looking at this sequence of x values approaching the number 3, and then we were plugging them into the function and looking at the corresponding y values and seeing, are those approaching a number on the y-axis? And they are, right? They're approaching 2. So that doesn't tell us what the limit is because we only checked one sequence of x values. To really know, we would have to consider all possible sequences of x values. And we can think about that. Maybe I approach from this way. I think we're going to get to that in the next slide, actually, so I'll save that thought. But what I was saying was this evidence supports the possibility that the limit is 2, right? But we should really consider all ways of approaching 3 on the x-axis. So here's another way where we start. This number x1 is about 2.3, and then our next number x2 is larger than 3. It's 3.4, and then maybe x3 is on this side of 3, and x4 is to the right, and we're sort of alternating back and forth. So that's another sequence of numbers approaching 3. And we want to look at the corresponding y value. So here's the first y value, second y value, third, and so on. And we just want to see what these y values are doing. And they are also honing in on this value of 2. So again, that's consistent with our belief that the limit should be 2. And by looking at this graph and thinking about, well, what can really happen, we get more and more convinced that the limit is 2. And so let's see what happens where a limit doesn't exist and how we can rigorously show that using this definition. So here's a zoomed in graph of sine of 1 over x, y equals sine of 1 over x, which is pretty funky. This is going up and down between -1 and 1 infinitely many times in this region that's 0.2 units long. So that's pretty crazy. And I claim that we can find x values, a whole sequence of them approaching 0, all of whose y values, when you plug them into the function, are equal to 1, right? So it's all the maxima of this sine of 1 over x curve. They're all the number 1. It goes all the way up to 1. So if the limit did exist, it would have to be 1, right? Because it has to be for any way of approaching zero, you get the same answer. On the other hand, we can find another sequence approaching zero where all of the y values are equal to -1. And so this would mean if the limit did exist, it would have to be -1. And it can't be two numbers at the same time, so it doesn't exist. And you could say this about any value in between -1 and 1. Could be all 0 or all 1/2. This function is sort of limiting on this entire interval. And so the limit isn't one single number, so the limit doesn't exist. So let's think about approaching in different directions now. Here's a graph we see as we approach the x value of 2. From the right, the y values are approaching infinity. What else can you get? Let me check on this mirror. And as we approach the x value of 2 from the left, this is a constant function that's just always 3, right? All those y values are 3. So if we approach from the left, we're just seeing the number 3. We approach from the right, we're getting all the way up to infinity. So that certainly means the limit doesn't exist, because we're getting two different things from the left versus the right. So these are the one-sided limits. And we're just thinking a little bit more critically about sequences here. What would happen if I approached in an alternating way from the left and the right? Maybe I'll leave that for you to figure out. Okay, so evaluating limits. So we've looked at a lot of graphs in the past few videos, and we're going to switch gears, start switching gears. We'll still use graphs, but we'll eventually want tools to just work by hand with symbols, and evaluate limits analytically. So we need some sort of ground rules or very simple limits that we just know automatically. For instance, related to the last slide, if we just have a constant function, it doesn't matter what x is, your function values are always that constant number. So if c is a constant, then the limit of c as x approaches anything is equal to that constant c. So that's a constant limit. And then if our function is just x, y equals x, this means if we have any sequence of x's approaching a, f of each x is just that same number. And so the f of all these x's is just the same sequence, the same x's. And so they're also approaching a. So if you look at this and say it out loud, it sounds very silly. The limit of x as x approaches a is equal to a, because as x is approaching a, x is approaching a, right? So it really is that simple. It's kind of a truism. All right, so that's the identity limit because that's the identity function, y equals x. Here is the graph to hammer that home, y equals x. As we approach 5, the limit is 5, et cetera, et cetera. For a constant function, here's y equals 4. Doesn't matter what x we're approaching, y is approaching 4. Okay, so some examples. Determine the limit as x goes to 3 of x squared minus 9 over x minus 3. So the first thing to notice is just that we can factor this numerator. It's a difference of squares, x minus 3 times x plus 3. So if we do factor that, we notice there's a common factor of x minus 3 in the numerator and the denominator. So For any value of x that's not 3, we would be able to cancel these because they'd be the same non-zero number. And this fraction, when you cancel, it would just come out to x plus 3. So f of x is the same function as just x plus 3 as long as x is not actually 3. When x is actually 3, we can't plug it in, so it's not even in the domain. However, we said in a previous video, if we're doing a limit as you approach 3, the value at 3 itself doesn't matter at all. It's completely irrelevant. So that means for any sequence of x's approaching 3, the y values are just the same as they are for y equals x plus 3. And so if your x's, this sequence here is going to 3. Now you add 3 to each one of those terms in the sequence. That's going to be approaching 3 plus 3, which is 6. So that limit is 6. And here's a picture demonstration of what this function is. So this, if you think of starting with x plus 3 and then multiply by x minus 3 divided by itself, that doesn't change anything numerically except the fact that I can no longer plug in 3. So graphically, that just makes a little hole in the graph and says 3 is no longer in the domain of the function, but everywhere else it's identical to the line y equals x plus 3. Using a table. So we can also gather data by using a table. Here's an example, another one where we can't directly plug in 0 into the denominator here because sine of 0 is 0, and we'd have a 0 in the denominator as well. That's like, we don't really know what's going to happen there. But what we can do is take numbers very close to 0 and plug them in. And you'll notice as you do that, and as our x's get closer and closer and closer to 0, these y values get closer and closer and closer to 1 from both the left and the right, and that therefore this limit is equal to 1. There is a more rigorous mathematical way to show that. It's actually one of the challenge problems, but I'm not going to get into that now because it's some pretty hairy geometry. Okay, so here's an example you can try. This is another crazy function. We took sine of 1 over x and multiplied it by x, and we're again looking at the limit as x approaches 0. So think about what the limit should be based on the graph. Think about limits of sequences, what they're approaching. Are they all approaching the same thing? You could also use a table to investigate this, but this is the try it yourself. And I'll put the answer there, but not an explanation. The limit is in fact 0 in this case. All right. Hope you enjoyed that, and see you next time.